second super important thing that you must know prior to the midterm is integration. Right? You know how to differentiate, you know how to use Taylor series. You now need to know how to integrate. Okay. Obviously, a similarity between integration and summation, right? Or what I refer to as an analogy. I think you know what we mean by when you find the mean of a set of data. The summation of all the data divided by the number of points, and it gives you the mean. If you have a continuous function, like a curve or whatever, then it's the integral of this. That's really the summation, right? Of all those things between the limits a and b divided by the delta, right? Between a and b. All right. That formula, as you well know, is used in a lot of scientific engineering applications just about everywhere. And I give you a little example down here where if you want to calculate the mass, it's the concentration times the volume. So when you think about it with regards to units, you know, you talk about a concentration. It could be a pound per cubic foot or whatever, right? Times a volume. Okay, so anyway, what we're doing is summing all of the concentrations and the volumes. And ideally, it means instead of discrete amounts that we're actually having continuous, an infinite number. All right? It's when it becomes discrete or finite that you use an approximation. All right? So if I write that out in mathematical parlance, then, that's what I get. It's just the integral. Now, it's a triple integral. Why? Because it's a volume. Right? What would it be if it's an area?
2.
2, right? How about one dimension? Yeah, how about that's where you get into theoretical physics and the infinite deep wells and quantum mechanics. I don't think they exist, do they? Okay, this is a graphical representation of the integral between of a curve, obviously between the limits a to b. And what you're doing, as you well know, you're calculating the area under that curve. Some examples that you may have run into. By the way, in the first figure on A, that's a mesh. And you will hear that later on when we get into some of the more advanced methods, particularly dealing with PDEs, partial differential equation, where you will have to create a mesh. And so we're approximating the outline of that river by that mesh. All right? And so you can see, what do I do about the boundaries right there? That's the tricky part. And that's the trouble you run into when you're doing things based on Taylor series, the differences. Remember the delta x's and delta y's? So we'll talk about that later when we get towards the end of the course about how you get around that. Here as a hydrologist, I need to know the cross-sectional area of the river, obviously, or a structural engineer, actually determine the net force on a building. Right? It turns out that the wind profile, by the way, is not linear. And a lot of times, some of the very simple approximations assume a linear profile, but it's not. It's a parabolic profile as far as wind. All right, this is what we mean by discrete versus continuous. So discrete is just a number of points. You have a point there, a point there, a point there, or wherever. And so you say, well, gee, what's the mean of that? So how would you find that? Right? Sum of all those points divided by the number of points gives you the mean. All right? What do you do when it's continuous? Now, you think of this as how many points are on that line? Think an infinite number. Okay. Under the umbrella called Newton Coach, you have a number of numerical integration schemes. And these are the ones that we will be getting into as the most common techniques. All right, so you take a data table, you can replace it by a polynomial in here. So, all right, what I've got here is that little n means I've got a discrete number of points. Right? And that approximation I can expand out as a series if I want. So if I go infinite, right, then I would have whatever the exact value would be, but I generally can't do that. All right, closed forms. Data points are known at the beginning and end. That's a closed form integration. Right? Remember that, circle that word, closed. Open. Open. Integration limits extend beyond the range of the data. When would we want to do open type of analyses? In forecasting, right? You have a set of data and you're saying, well, what happens in the future, or if I continue this? That's the forecasting part. Okay, approximation of an integral by the area under a straight line. All right, if we did that, you can see, well, what happened to all this? I didn't capture it completely. Right? What happens if I do a more appropriate or higher order approximation? Now it's a parabola. I've captured more of the area, the true area here. So I might be a little over right here, a little under there. Probably balances out. All right, approximation of an integral by an area under the 3 straight line segments. So let's think for a moment. If I use short enough segments, then how close can I come to approximating the curvature of this thing? Pretty good, right? If I use little bitty ones, it means I have a lot of them. If I use big ones, then my approximation isn't going to be very good. So here's an example of using just 3 linear segments. All right, so that's not too bad. All right, now I can obviously improve that by using more segments. Okay, difference between a closed and an open integration. So endpoint, right? So here's the area under this particular segment of that curve, and I defined it to be within those endpoints. But over here, this is open. So maybe I'm interested in, gee, what would happen here or what would happen down through here? Yeah.
Wouldn't you have the one on part A though?
Right here?
No, graph B, wouldn't you have the endpoint near A?
Oh, I may not.
You may not.
I may not. That may be the only information that I have, are those endpoints right there. So I'm trying to infer what I think might be happening later on. Well, that gets more into the stochastic part or the forecasting part or the statistics part. But we'll talk about that later. Okay, first rule. Circle this one. This one's important. It's called the trapezoidal rule. It's the first of the Newton-Cotes closed integration formula. All right? So let's take a look. The integration is equal to integral, obviously, a to b. The function evaluated at a, the first endpoint, the value at b minus the value at a divided by b minus a times however segments I've got. Well, it turns out I can rewrite that so it looks like that. All right? That's the formula. Okay? So that's equivalent to approximating the area of a trapezoid under a straight line. So if you notice in the area, what was that figure, that segment, with that straight line that was going up like this? That was a trapezoid. Right? So that's exactly what you're doing, just finding the area of the trapezoid. All right, now the area associated with the trapezoid is this. All right, how did we find that? Just like you do Taylor series and truncation, same idea. All right, so that tells me what order accuracy is this approximation. The key is right there. Okay, so function being integrated is linear. If the function is linear, the trapezoidal rule will be exact. Okay? Rarely do you have that, but if it were, it would be exact. Second derivative of a straight line is what? 0, right? Functions with second and higher order derivatives, there will be some error. Right? Understandable, because we're using a linear approximation. Okay? And that's what you get. All right, so here's the true function. Endpoints A and B. What I've done is say, okay, I'm going to integrate between these 2 points, and this is the trapezoid that I have. All right, take a look at an example. Here's a function out to the 5th order on this, and we're going from a equals 0 to b equals 0.8. Okay, so we evaluate f at a equals 0, which is equal to 0.2, and f at 0.8. These are the values that we get. All right, plug it into the equation, we get 0.178. The error, I just put it into that little formula. What do I get? It's about 90%. Right, so what does that tell me immediately?
It's not linear.
What else? You guys try this. Don't light up your cigar just yet. It probably implies that my segment is too large. All right, so what I may have to do is a whole bunch of these things, right? And remember, if I'm trying to approximate the curve or the function, the smaller the increments I have, the closer I get to the true approximation. All right, what's the second derivative? Take the derivative of this. Get that, the average value of the second derivative, minus 60. What's the error on that? Okay. It says, ooh, well, I've got second, third, fourth derivatives that I can get out of this thing. It's not linear. So immediately I wouldn't think that this approximation would be the best choice for trying to approximate something that looks like that function. Okay, so there's a graphical depiction of this thing. And so what I did was to say, okay, I'm calculating from here to here. There's the estimate. And that's what the function looks like. See all the rest of this? You know what it's called. Okay, here is an M file that you can use for the trapezoidal rule. And as you can see, it is not very long. Right? So it's fairly short. Okay, here's the function. Well, here, let's look at this. Here's an example. So here is x with these values, x up to here. Here's the function that we just saw. All right, we'll call trapezoidal rule. Answer 1.59. So it's actually 3 lines of code. Right? Now, what happens if you want to start using multiple integrals? Okay, so you've got an integral within an integral. So you've got a method within a method. In the old Fortran coding days, that was known as interior do loops. Okay, numerical evaluation of a double integral. This is a 2-segment trapezoidal rule. Now let's see if you can figure out what's going on here. What are we doing? Going there, and we're going there, right? So take a look. You're evaluating in one direction and then evaluating that, right? So you're integrating an integral, right? It's an integral within an integral. Fortunately, computers just love that because that's so simple. Might be difficult for you with pad and pencil, but for the computer, it's easy. Right? Now, composite trapezoidal rule. So you can improve the rule, right? And you can divide the integration interval into a number of segments. And that's what I was referring to. By saying instead of just one big overall segment, you're going to break it down into a series of these things. And that's basically what's going on here. Here's a segment, here's a segment, here's a segment all the way out. Right? Each of these segments is going to be defined by the limits of the integration of the segment. All right? So substitute the trapezoidal rule for each of those integrals, and this is what you get. All right? Now that means dot, 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 remember? So if you go all the way out to the end, that's what you get, whatever the end will be. I can rewrite that into a very simple form like this. This is the one I want you to remember because you cannot keep track of all these things, but this is the one. So here's the first endpoint, here's the last endpoint. All you have to really remember is, well, what's going on in the middle, right there. So I equal 1 to n minus 1, 2 times whatever those things would be, right? These terms. That's how you do it, all right? If I want to know the average value of the second derivative, I can plug it into this relation. Here it is right here. And now you see what I have. Okay? So what it means is that my error has been improved. That is, I've decreased the error by doing multiple intervals. Okay, remember what that looked like before? So we had, here was the solution. Now if we do this as a series of segments, even though they're linear, what have we done? It's beginning to more closely approximate the true nature of the function. So we do much, much better. Okay, let's use the two-segment trapezoidal rule to find the interval 0 to 0.8 of the function that we looked at before. All right? So we have how many intervals we're going to use? 2. All right? And so we're going 0 to 0.4 and 0.4 to 0.8. All right? So we evaluate the functions at those two sets of endpoints, right? So 1, 2, 3. Plug into the equation. Now it's 1.06. Our error is now about 35%. Just doing 2 segments. So we've cut it less than half by doing the 1 segment. All right? That's better, obviously. Use more intervals, you get close to the exact solution. If I use 10 segments, we get 1.61. Now we're down to about a little less than 2%. As the number of segments is doubled, the truncation error becomes quartered. Right? So if you look at the truncation, the remainder, that ET, you'll see that every time you as you double the segments, it reduces it by 1. All right, here's an M file to implement the composite trapezoidal rule. All right, as you can see, endpoint, intervals, all right, fairly straightforward. Okay, circle trapezoidal rule. You know how to do that, a 1 segment and a multiple segment. Those 2 equations. This is the second method I want you to know. This is called Simpson's rule. And this is a more accurate integration estimate. Obviously what you're going to be doing is to increase the order of the polynomial. Okay, so there are 2 Simpson's rules. The first is the 1/3 rule. Notice in red what I have. The 1/3 rule, limited to an even number of segments. Equally spaced, all right? Even number of segments. 1/3 rule. Make a little note there. Must be even number of segments. Simpson's 3/8 rule. Odd segment, even point limitation. All right?
What does that mean?
Now, you'll see the example, basically what's going on here. You must have an odd number of segments, all right? Even number of segments. Now you say, why is it that I want to use the 1/3 rule? Why is it I want to use the 3/8 rule? Okay? Because of the accuracy improvement that you get from this, okay? 1/3 rule simply means that h is divided by 3 using a second order polynomial. That's all it is. 3/8 is a third order polynomial. All right, you fit to 4 points. All right, you'll see an example. We'll run through this. All right, the second order polynomial is used for the 1/3 rule. So here's what that polynomial would look like: first term, second term, third term. All right, I can rewrite this into this brief form. You notice h, the intervals are equally spaced, they're the same. All right, first value, endpoint, right? There's that value, there's the last endpoint. B minus a divided by 2 is the h, all right? That's the interval. Here's what these mean with regards to a's and b's and x's, all right? I can rewrite this so it looks like this. All right, so if I don't know what the h is, but I know what the endpoints are, then it's b minus a, then this equation, which is right here, divided by 6. Here's the error. Now take a look at the error. Remember what it was on the trapezoidal rule? It was h to the what? Third. What is it here? H to the fifth. All right, so I've gained 2 orders of magnitude. Okay. All right, oh, I can rewrite that so it looks like this. Right?
What is that saying?
This, it means it's somewhere in the interval between A and B. All right. Okay, this rule is more accurate than the trapezoidal rule. It's 3rd order accurate, even though it's only using 3 points. It yields exact results for cubic polynomials. The interesting thing is that it really stems from a parabola or a quadratic, right? Approximately 2nd order. Okay, let's go back to that function again. Here's f of x equal to 0.2, blah, 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 all the way out to 400x to the fifth, right? We're going to integrate from 0 to 0.8, right? 2 segments. So h is equal to 0.4, right? Between 0 and 0.8. Here's the functions again. So plug into the formula, I get 1.36. What's my error now versus what I got for the trapezoidal rule? Remember what the trapezoidal rule was for the 2 segments? It's about 35. See what the Simpson rule gave us? About 16. All right? Here's the second derivative, average value, blah, blah, blah. Okay. So you see, for the same amount of work, you can get a much improved accuracy. Okay, composite Simpson's rule. Likewise, if I want to do it with a lot of segments, basically I would just, okay, I add up all these various segments. Substituting Simpson's 1/3 rule into each of these, you'll notice, oh, okay, I see kind of the same formula every time it goes through here. Or I can rewrite it into that recursion form. That's the one I want you to retain. That's the one you can remember. All right, so in point, right? Notice 1, 3, 5, 7, 9. What's this? The odds. 2, 4, 6. What's this? The evens. Okay, and then the endpoint. All right, number of 3 times the number of endpoints. All right, the error that you get, obviously, as we said, is 3. All right, so that's the composite part. All right. This gives you an example of what's going on as you do the calculation with the various segments, employing Simpson's rule as we go along the function right here. So you see, here's the first one. These are the weights that would be associated with those points in that integration. First segment, second segment, third segment, fourth segment, right, fifth segment. I think you see what's going on. It does a very good job of approximating that function. Okay, circle back Simpson's 1/3 rule. Know how to do that. Now, the 3/8 rule. Okay, let's take a look. Here's the simple formula. Here's the endpoints. Notice 3f of x1, 3f of x2. H is now b minus a over 3. So you see where it's called the 3/8 rule? 3/8 shows up right there. So just remember 3/8 rule. It's 3/8 times h, the interval, then times that expression. All right. So the error now that I get here, it's still the fifth, but you notice the denominator here, it's significantly larger. So the error is quite a bit smaller. Okay. This rule is more accurate than the 1/3 rule, but now what? It requires 4 points where you had 3 points in the 1/3 rule. So that's how you can remember. 1/3 rule, odd. 3/8 rule, okay, even. So you get your intervals correct. Okay. This I find pretty interesting. You can do a combination of the 1/3 and 3/8. That can overcome limits of either the even or odd segments. By the way, you see, you're not constrained to use one method. You can do a combination. You can use a trapezoidal rule. You can combine it with a 1/3 or a 3/8 Simpsons if you want. Just depends on the segments or what you want to do with regards to certain parts of the function that you're trying to integrate. Okay, numerically integrate this function again from 0 to 0.8. Simpson's rule, here's f of 0.2, f of 0.6, okay, and here are the values of the functions at the interval points, right? Plug it into the equation. 1.519, what's the error now? About 7%. What was the error on the 1/3? About 16, so it's cut it in half again, all right? Okay, the graphical depiction of Simpson's 1/3 rule for the area under the parabola. If you're connecting 3 points, let's assume that we have these 3 points that we're connecting. Well, that's the approximation that we're using. Okay. Not too bad, certainly better than trapezoidal. Right? Here it is if I'm using the 3/8 rule. So now you're using a cubic equation connecting 4 points. So instead of 3 points, I now have 4 points. So, oh good, I can take that point in there and use that point. Now I do, obviously, a much better job of approximation. So remember, 3/8 rule, think of it as a cubic. Okay, so you can now apply them in tandem if you wanted to handle multiple applications where you had an odd number of intervals or combinations thereof. So you see, here's an example of that function that we saw. This part is the 1/3 rule. Well, that's fine. I've got 3 points to do that. And then here's the 3/8 rule. So I'm going to use that point, that point, that point, and that point. All right, multiple integrals. Now let's assume I want to find the integral, this double integral of this function. And I can rewrite it or expand it. So I've got this inner integral from C to D, and then I'm integrating that from A to B. All right. By the way, does it matter which order I do this in? Doesn't matter. As long as it gets integrated. All right. So here, let's let A equal 1.5, B equal 0.2, C 0.2, and D 0.6. Let's use the trapezoidal rule here, where y equals 0.2. We'll plug it into this expression. Here's the little formula for it. All right. At y equal to 3, I would plug that in right here, y equal 3. That would be the formula, and so forth and so on and so on. Y equals 0.6, so forth and so on. It's the same, repetitive. Okay. Now apply Simpson's 1/3 rule in the y direction. All right. So what I've done is do the integration in the x with the trapezoidal rule. All right. So I do all of these at these particular values. Now I'm going to take those and treat those as points, just like I would in an integration of Simpson's rule. Here I'll apply the 1/3 rule, so h over 3, and then here would be the values that would be coming down from here. All right? Interestingly, this can be done in a simple matrix formulation. So here's the double integral. If I think of it like this may be the easiest way to try to do this. All right, so let's take a look. Here's the delta y divided by 3. Here's the delta x divided by 2. All right, so this is the trapezoidal, and this is Simpson's 1/3. All right. Notice these terms right in here. Where do these come from? Where do those things come from? They're the coefficients that show up on these expansions. All right? So you can actually create a very simple matrix. Now, this is a dense matrix, so how would you solve this? What would you use? Sure. Some sort of elimination technique. Okay. Double integral is the area, or as you know, the area under the function. So in 2 dimensions, right, it would look like this. It would be a surface. Okay. continue reading about integration. Thursday, we're going to go over Romberg integration and Gauss quadrature. Now, the most important of all the integration schemes is Gauss quadrature. The reason being that that is the most commonly used method in the commercial codes. Right? Nearly every commercial code that requires some integration scheme is going to be based on Gauss quadrature. And you're going to see how clever he was in coming up with a very simple trick to do integration that's as accurate or better than the methods that you saw here. Okay, so integration schemes. Trapezoidal rule, Simpson's method. Which two Simpsons? 1/3? 3/8? All right? Yeah. Okay, question?
Sir, you can post like a practice exam or a review sheet?
Yeah,
for- for the-
next Tuesday will be reviewed. All right, so we'll do a lecture Thursday on this. Then a week from today, we will spend time reviewing what we've covered so far.
So the test is next.
Next
The
Thursday?
test is next Thursday, a week from Thursday. Okay, any other questions?